And I want to share with you a screen just to show you what we got left to do this semester in the last 2 days of class and what homework you have due this week. So I'm going to share with you my Google Chrome, and you should be seeing our Canvas page. And if you look, we have pretty much done this stuff up here. Okay. Today and Wednesday, I'm going to be working through these 2 sets of notes here. There's at least one more worksheet. This is 2 problems and an extra credit on worksheet 32 and 32 and 33, which are combined here. And then there's a homework which is due on Friday. I will tell you this, depending on how far I get on Wednesday, I may have to delete one of the homework problems. I know that'll break everybody's heart, but it just depends on how far we get in class on Wednesday. There's 4 problems in the homework for this week. If I don't quite get through all the material I need to do on Wednesday, I may have to delete one of them. Similarly, there may actually be one more short worksheet. Worksheet 34 may come up again, depending on how far we get on Wednesday. And that 4th worksheet will be due on Friday. In fact, everything this week, you can kind of plan on being due on Friday. Friday's a reading day. There is no class on Friday, but I will be available for office hours if you let me know when a good time is for any homework questions. I'm also available on Thursday all day. I don't have a lab this week with my 101 students. So if there are any questions on what we go over today and tomorrow and Wednesday, which is in the homework that's due Friday, or the worksheets, which will be due Friday, just send me an email saying when a good time is, and I'll make an announcement for when office hours are. Otherwise, I'm just picking numbers off kind of randomly. All right, so I'm going to stop sharing that with you, and we'll see who we got. 7. We're up to 7 people now, so that's a little bit better. I'm going to stop sharing this and move on to what we were doing when we broke before Thanksgiving, which was Schrodinger's wave equation in 3 dimensions as it applies to the hydrogen atom. And so I'm going to shift over to sharing my Notability on my iPad. And let's see if I can get it to screen mirror. It worked this morning. Yep, looks like it's working again. Put that away. And we were talking about Schrodinger's equation in spherical coordinates. And I should maybe back up just a little bit. You know, Schrodinger's wave equation is the Newton's second law, I guess, of quantum mechanics, modern physics and quantum mechanics. And you'll see it again. So let's really start from kind of first principles and just make sure everybody's clear on what we did. All right, it's working. Schrodinger's equation in 1 dimension, minus h bar squared. All right, my pen is going to be, there we go, moving better now. Not much better though. There, 2m. Okay, and then we had the second derivative of psi with respect to x. And remember, in 3 dimensions, those have to be partial derivatives because, well, psi is a function of r and theta and phi in spherical coordinates. In Cartesian coordinates, it'd be just x and y and z, but we'll see what we're going to do here in a second to replace that, plus some potential energy function times the wave function. And the potential energy function I expect for a hydrogen atom, where there's a plus sign there and some minus electron going around it, I expect a Coulomb potential that looks something like K charge on either one of those 2 guys squared over R, perhaps with a negative sign as well, because it's an attractive potential between the 2. In any event, that's equal to the total energy times the wave function, okay, and that would work in 1 dimension. For the case of the hydrogen atom, in 3 dimensions, we make 2 changes. The first thing we do is we recognize that mass there, which would normally be the mass of that electron going around the proton, that's not the best the best answer for what the mass is. When we talked about Rydberg's modifications in the Rydberg equation, we replaced m with the reduced mass mu, okay, which is the product of the two masses divided by the sum of the two masses. So we're going to do exactly the same thing here, minus h bar squared over twice the reduced mass. We're going to replace that second derivative, which I wrote as a partial, with the Laplacian of the wave function. And then it's kind of conventional to bring that over to the other side of the equation. A lot of people like to do that and set it equal to 0. The reason is, I guess, a guy named Helmholtz, who worked equations of this sort, he liked having everything equal to 0 on the right side. And so just moving that over does that for us. Okay, last kind of little mathematical manipulation that is typical when you're looking at Schrodinger's equation is to clear those constants out. And so the Laplacian of the wave function, I guess I'm going to write it as plus h bar squared over twice mu, but since I went plus instead of that minus sign there, I'll just reverse the order of these two guys, have the total energy minus the potential energy times the wave function is equal to 0. And then I think I'm in business here. And in spherical coordinates, what does the Laplacian mean? Well, it's this big long thing right there. And truthfully, it's something I don't have memorized. I look it up whenever I need a Laplacian in spherical coordinates. I go to a math book, but that's what that means. And notice it's operating on psi. And then, of course, this term right here goes right to there. And so that is Schrodinger's wave equation in 3 dimensions. We're thinking about a hydrogen atom here. That's what we got. There's Schrodinger's equation. How do we solve it? And we did this, we started this, I guess, on Friday before Thanksgiving break. We said, well, we're going to use a technique known as separation of variables. We're assuming this wave function here, we're assuming the wave function can be written as a product of 3 functions. Each function is only got in it the variable r, for capital R, theta for the function f, and phi for the function g. And that's why we call this separation of variables. We're hoping that our solution for psi to Schrodinger's wave equation will be a math function that can be made up of 3 different functions multiplied together, each a function of only 1 variable. And so here might be an example of this, right? I might have r times theta squared times phi or something like that, right? This is what I'm calling r. And by the way, this isn't a solution. This is f and this is g, okay? And so we're multiplying them together. I'm going to erase that because I'm only trying to make the point of what, how we're separating out variables. At least we're hoping our solution is separable into each of the 3 coordinates. All right, and so we manipulated this thing, Schrodinger's wave equation, on Friday before Thanksgiving, and we left off with that thing. And I just want to remind you of where that came from, okay? If I'm taking the derivative of psi with respect to r, and I've separated out psi into f and g and capital R, well, when I take the derivative with respect to r, I only have to take the derivative on the function r, and f and g functions are constant with respect to r, so they just slide right by the variable. Right, I'm sorry, slide right by the derivative. Same thing over here. When I take the derivative of psi with respect to phi, only f has any functional relationship to phi, so r and g are constants and slide right past the derivative, okay? And I guess the same thing with g, like for whatever reason, I decided to show a second derivative there because ultimately that's what I'm going to need in my Laplacian. If you look at the form of the Laplacian, sure enough, it has a second derivative with respect to phi, but you do the first derivatives on f and then you multiply something out, and then you take another derivative. Same thing with R, you do a first derivative, you multiply, and then you take a second derivative. And so that's why those are the important steps. Okay, well, we put all those things in to Schrodinger's wave equation in spherical coordinates. Okay, and then we did some mathematical manipulation. We said, all right, let's divide everything by the wave function, R, F, G, multiply, just divide those things away. And so you can see things start to simplify out. Like in the first term, if you divide by R, F, and G, you'll cancel the two things in the numerator and you'll only be left with a thing in the denominator. And then with an eye towards clearing that thing right there, we decide to multiply by R squared sine squared of theta. Okay, and once we're done doing that, you'll see that this term right here, which was the term we were most concerned with on Friday before the break, it will just have 1 over G times the second derivative of that G function with respect to its variable. And that's what we were looking for. Okay, we wanted to separate out a term that only has one of the three functions. In this case, we're going to go G first, and its variable and nothing else. So that's what I did. I brought it to the other side of the equation, and I guess it came over as a negative sign, but if you'll notice, I made everything on the left, I made it negative. And what we did on Friday before the Thanksgiving break was we said, well, the only math functions I could come up with that could possibly solve this equation, well, is if I let the left side and the right side be equal to a constant. And oddly enough, the constant I chose was the mass, an M, okay, which is not a mass. It's just an index, just like when we were doing the cubic problem or the rectangular box problem, we had an index N1, N2, N3. Well, here in spherical coordinates, we define the constant, the index we want to be, just M sub L, for reasons that'll hopefully be clear by the end of class on Wednesday, and we set it equal to that thing squared. And the reason is, I guess, because this is something that we can solve pretty easily. Okay, that if I let, well, let's slide back so you can see what I kind of did here. If we look at these two terms right here, okay, the constant and the right side of the equation, and we set them equal to each other, well, the answer we showed was G is equal to e to the I M sub L times phi. Okay, and if you don't believe that's true, because differential equations is in your future rather than your rearview mirror, my challenge for you is, okay, take the second derivative, plug it right in on the left-hand side, take the function itself, put it in on the right-hand side, and see if that doesn't make the equal sign valid, if it solves the equation, is what we said, and it does. Now, some of you may worry about, well, why didn't I go with a negative sign? Well, one of the things we showed was, since G has to be single valued, that means it has to have the same value when phi is equal to 0 or when phi is equal to 2 pi, okay, because phi just comes all the way around one cycle. It has to have the same value at that point, and that required that M sub L be an integer. It could be negative, and so if it's negative, that takes care of that, doesn't it? All it has to be is an integer, and a negative integer is a possibility. And so that's why we went with the positive I M sub L phi as the solution for G before we took a break. All right, any questions on that? That's I guess the 15-minute review of what we did before we left. And now we got to launch off on the new things. So if there are any questions, now is probably the time for them. All right, great. Then we're going to move on with that then, I guess. And repeating the G function now. Okay, remember then that what we did is we said, come on, pen. Now it turned itself off. Of course it did. This is equal to minus M sub L squared. Odd name perhaps, but it's what we've got. And we've taken care of that piece. And so now what we're gonna do is we're gonna try to do the same trick of separating variables right there, okay? And if you look, this term right here, boy, if I could just get rid of that sine squared piece, it would only be a function of r. This first one here, if I can somehow get rid of the sine squared as well, it would only be a function of r. This last one, the third one, oh, let's see. It looks like right now, it's only a function of theta, isn't it? Now, here's what we're going to do. I guess we're going to take that guy, and I'm going to turn everything back to positive, okay? Because it looks to me like sine squared of theta. I got an r here. And I just got the sine squared. I got to get rid of that sine squared somehow, don't I? That's what we got to do. So let's work with it a little bit. R derivative with respect to r of r squared, derivative of the function r with respect to the variable r, plus 2 mu over h bar squared, r squared, sine squared of theta, total energy minus potential energy, times, I'll swap over my glasses here so I can see things. Oh, let's see, minus, plus, turning it positive, sine of theta over f, derivative with respect to theta of sine of theta df d theta. All of that's got to be equal to, I'll put it over here, minus m sub L squared, because that was the constant we needed on the G side. Oops, that goes positive as well, doesn't it? So all I've done is turned everything positive there and given myself the equation I need so I can scroll on up. Okay, I think what I want to do to this thing is I want to divide through by the sine squared of theta, right? Just kind of looking at it, if I get rid of that, I can get rid of that. I might be in business here. So let's do that. M sub L squared over sine squared of theta is equal to, I guess I've got 1 over r, the derivative with respect to r of r squared dr plus twice the reduced mass over h bar squared, r squared, divided the sine squared away, total energy minus potential energy, okay? And now here's the term I guess I want to be careful with, because I'm dividing by sine squared, so that'll leave me 1 over f. Sine of theta goes down to the denominator, derivative with respect to theta of sine of theta df d theta. All right, I think I've kind of hit the mark here, because those two terms right there are only a function of capital R, or the thing it's a function of, little r. And this equation, this term right here in the equation is only now a function of theta by virtue of what I did. So let's bring it with its buddy on the other side of the equation. And so I guess I've got m sub L squared over sine squared of theta minus 1 over the function f. Remember, f is only a function of theta. 1 over the sine of theta, derivative with respect to theta of sine of theta, derivative of the function f with respect to theta, has to be equal to what's left, the two things that I put the square bracket around. That's 1 over r times the derivative with respect to r of r squared dr, derivative of the function r with respect to r, plus twice the reduced mass over h bar squared, r squared, E minus B, total energy minus potential energy. All right, mission accomplished, I think. On the left, I have terms which are only a function of f of theta. So I have the variable theta or the function f. On the right, I have terms which are only a function of r or the coordinate r. So here's the separation of variables question, which you'll always be asked. Can you think of two functions, f, which is only a function of theta, and r, which is only a function of r, so that you can do all these mathematical manipulations on them and still have the left side be equal to the right side? And the answer, according to the mathematicians, without proof, is that the only way I can do this is if the left-hand side and the right-hand side are both equal to constants. That's the deal. And just like minus ml squared was kind of an odd constant to get that phi equation, the g of phi equation, well, you're going to have an odd constant here. It turns out, and I think I just mentioned this before we took a break, the constant you're going to use is L times L plus 1. And I didn't do it. The two scientists, mathematicians who were responsible for these equations made this designation. If you think about it, though, if L is a really big number, this is kind of like L squared, right? It's like taking 4 times 5. So you're not exactly squaring it, but it's a similar sort of idea as some constant squared. All right, the equation that we're going to work with today primarily, and I may get to the other one as well, but we'll definitely get this one, is what we call the angular equation, the angular portion of Schrodinger's wave equation, because I think I can say that m sub L squared over sine squared of theta minus 1 over the function f, which is only a function of theta, times 1 over sine of theta, times the derivative with respect to theta of sine of theta, derivative of the function f with respect to theta has to be equal to L times L plus 1. And so it's common then to make one little kind of correction here, one little modification. Let's multiply this guy by f, multiply that guy by f, multiply that guy by f. And in this form, let's see, manipulate just a little bit further, I guess. Let's go make this term positive. So 1 over sine of theta, derivative with respect to theta of sine of theta. Take that term, make it positive. And so that then will bring this guy to the other side of the equation to combine it with that. And it looks to me, I want to make sure I've got two negative signs here that I've got to get out. Okay, I made this positive, this negative, this negative. And then when I bring that guy to the other side of the equation, it's going to be minus the quantity L plus 1, my separation constant, minus the other guy, this guy over here, m sub L squared over sine squared of theta. Those are both multiplied by f, so I'll factor it out, and that's 0. All right, this equation has a name. It is called the associate Legendre differential equation, after the scientist who solved it, mathematician perhaps, who solved it. And so hopefully I've got it written in the right form. I can blast off right to there. That should be the equation that I just manipulated to on the previous, with all my chicken scratches on the previous page. And so Legendre worked this. And by the way, if you notice, there are a lot of mathematicians, scientists, natural philosophers from the 1800s with French last names. And it shouldn't really surprise you that that's because Napoleon believed that investing in science and mathematics would make his country stronger, more warlike, more economically prosperous. So he invested in a lot of this stuff. And so as a result, you'll see there's a lot of prominent mathematicians and scientists from the 1800s who were funded by Napoleon to do their work, Legendre being one of them. Legendre spent a lot of time solving this equation and a simpler one called the Legendre polynomial. Okay, but this is the associated Legendre polynomial. And his life's work is to come up with the solutions to this thing. And they're designated, okay, we're solving for f, right? That's what this differential equation is all about. It's really a second derivative of f plus a whole bunch of constants, I guess, and the function theta multiplied by f. And Legendre solved this thing. This is the form, that should be a theta right there, cosine of theta. The function that solves that are the associated Legendre equations, and I've listed them right here, okay? And you can see that they have two indices, which are written L and M sub L, which are in the equation right there, and of course, right there. And so Legendre just worked through this, okay? When L is equal to 0 and M sub L is equal to 0, what will solve this thing? Well, it's probably not too surprising. 1 is going to work here, okay? But then he said, all right, well, what about when L is equal to 1? Okay, so now I'm taking 1 times L plus 1 right here, right? This term becomes a 2 then. And he went, all right, well, let's let M sub L be 0, and let's solve the equation right there. He gets cosine of theta. And then he runs through again. He goes, all right, well, let's work it again. This time we'll let L be equal to 1. And he said, instead of making M sub L be equal to 0, let it be equal to 1. And the answer turned out to be minus sine of theta. Interesting thing, though, when L was 1, and he tried to let M sub L be equal to 2, well, there was no solution. And so all of a sudden, in this solution set that Legendre has made his life's work, there is a requirement that M sub L here must be less than L, well, less than or equal to L. And you can see that you can go to 1, 1, but you can't go to 1, 2. It just does not exist. Legendre was not able to find a solution, a mathematical function that would solve this differential equation. All right, well, you may go, how do I know? Well, I'm going to give you an opportunity. That's one of the worksheet problems. I have you check out the 1, 0 solution, this guy right here. Take the derivative, take the function right here, multiply by sine of theta, take the derivative again, divide by sine of theta, and see if, sure enough, is it solved? Does that guy 1, 0 solve what I call the angular part of Schrodinger's wave equation in 3 dimensions in spherical coordinates, when what we're doing is we're thinking about a hydrogen atom? Okay. Any questions on that? And you can see there's a whole bunch of other solutions as these things get more and more complicated. Now, I don't know about you all, but I can't picture what these functions look like. You'll see them again. I know a couple of you are taking the advanced electricity and magnetism course with Dr. Kem in the spring. You'll find a similar differential equation to this one, only it won't be the associated Legendre equation. It'll just be Legendre's differential equation. And you'll see solutions. You'll just accept them, I think, like you accept that the solution to Helmholtz's equation is sines and cosines. They're just a series of mathematical functions that a very prominent mathematician worked out because it solved a relevant physics problem. I've written them out here in the blue box, but I want to make a point about these things. Okay, so these guys, the f functions, we say are the associated Legendre polynomials. Okay, remember this thing right here, and it turns out, according to Legendre, they're a function of cosine of theta, not just theta, interesting enough. This guy right here, the g function, we said at the start was e to the I m sub l times phi, the other variable, okay? Well, people have done some simplification because it always seems to work out nice and define the product of these two guys as another function known as the spherical harmonics. And the symbol for them is capital Y. It's just the product of the f function, which are the associated Legendre polynomials, which are tabulated. I listed right there. And then multiplied by the appropriate value of the g function. Okay, and you can see that there is an m sub l there, and there's an m sub l there. So these two are linked, okay, as you write them out. And very often what you have tabulated is this capital Y function. And where do I have it here? Yep, there they are right there. Okay, I've given you all the first couple of normalized spherical harmonics, Y, which is the product of f of theta, the associated Legendre polynomials, and g of phi, which is what we solved before the break. And you can see then somebody's gone through and normalized them. So while the first one here is 1, okay, and let's see, if phi, or I'm sorry, if m sub l is equal to 0, then the g function is also equal to 1. Well, you've got to normalize it too, though. So it turns out that the constants with normalize it is 1 over 2 square root of pi. I don't want to get ahead of myself. We will talk more about normalizing on Wednesday. But what does it mean to be normalized? Well, just like in one dimension, you've got to take the wave function's complex conjugate, multiply by itself. Okay, in one dimension, we wrote dx. It should make sense to you that that's not what we're going to do in 3 dimensions. We're going to write dv, okay? And in spherical coordinates, that's a triple integral. Psi star psi, and the volume element in spherical coordinates. Hopefully you learned in your multivariable calculus class. And we talked about it on the worksheet I worked through right before the break, r squared sine theta, dr, d theta, d phi. And so that integral right there has to be equal to 1 for both, well, or what I'm saying is y, the spherical harmonic. So y star y, in this case, would be what I need, but there's something missing, isn't there? There still has to be an r star r. We've only taken care of 2 of them right here. Well, it's conventional to work with that guy and that guy and that guy separately from the angular pieces, which is that, and these two. Work them out separately. The normalization constant, if you work through that, 1 over 2 divided by the square root of pi. All right, more on normalization to follow. You can see it's a great mathematical drill. And that will be, I think, your second worksheet problem is once I work through the solution that we haven't talked about yet, what is R, well, to see if these things are properly normalized. All right. I do want to show you a little bit about what these things look like, these spherical harmonics. And what we've shown here is that right there, that's the L equal 0 case, okay? And it's just a sphere, isn't it? Because in spherical coordinates, if you let phi go from 0 to 2 pi, all around from the x-axis to the y-axis to the minus x-axis to the minus x-axis back to the y-axis, and it's a constant, well, that's just going to be a circle. And if you let theta go from the North Pole, where theta is equal to 0, down through the equatorial plane, down to the South Pole from 0 to pi, well, a constant will just be a spherical ball of radius 1 over the square root of 2 square root of pi, right? The next row down on these shapes is L equal to 1, and that's those two guys. The reason that there's two of them is that it is possible for M sub L to be plus or minus 1. We said Legendre found if he went to M sub L equals 2 when L is equal to 1, he wasn't able to find a solution. He was able to go in the negative direction, and when L is equal to 1, when M sub L was minus 1, there was also a solution. And so those are these two guys. This is the M sub L equal to 0 case in the center. This is the M sub L equal to plus 1 over here and minus 1 over here. And you may have seen shapes like this if you've ever taken a chemistry class. The chemists draw pictures like this to show where bonds are going to be happening between two atoms. Well, we're just talking about hydrogen here. And remember, these wave functions give you the probability, if you square them and normalize them properly, of where the electron is most likely to be found. Working down here a little bit, the next guy down is L equals 2. And you'll see there's 5 such cases. M sub L equal to 0 in the center. M sub L equal to plus or minus 1 on either side of that. And of course, this is plus 2 and this is minus 2 on that next row for L equals 2. And then just for fun, you can see they get more and more complicated. This is the mathematical formula in the column here in the light blue, and this is somebody's depiction of what the math function looks like. And all they're doing is they're drawing it at a particular value. Okay, so that's what the functions look like. And I got this, of course, from brilliant.com, a great little website if you want to see mathematical functions and what they look like. But these have physical significance in how bonds and chemistry seems to work out. All right, I think I want to, a little bit more. If you do square these spherical harmonics, one of the things I do want to point out is what will happen, for example, to this term right there when you multiply by the complex conjugate. Well, if you multiply each of those by the complex conjugate, you'll have something that goes e to the plus I phi multiplied by something that looks like e to the minus I phi. And so that's going to be equal to 1 because the exponents add. You've got e to the 0 in each of those cases. It even happens right there, okay, and right there as well. And so you lose your dependence on phi, don't you? All of a sudden, that's the angle phi. There's your x-axis, there's your y-axis, there's phi. All of a sudden, when you square these spherical harmonics, square by multiplying the complex conjugate by the function itself, all of a sudden you lose the variation in the phi direction because it just goes to 1. And so if you're looking for what the probability is, well, for the simplest case, L equals 0, M sub L equal to 0, it could be anywhere with equal probability. But if you're looking for the electron now in the L equals 1 case, well, there you can see where the probability is most likely. If it's in the M sub L equal to 0, that's M sub L, as opposed to M sub L equal to either plus or minus 1. Again, both of these is for the case L is equal to 1 as an index. Now, this may seem more complicated than what we did for the particles in the rectangular box, which you all submitted before Thanksgiving break. It's only because of the fact that you're working in spherical coordinates instead of Cartesian coordinates. But there are these shapes, these probabilities. You may recall most of you drew little boxes and you said, well, where's the thing most probable to be? Well, right there. Or then the next one up, you drew a little box where it's most probable to be there or there. And then you all drew nice little pictures for me. These are exactly the same thing, except the indices aren't really nice, like 1, 1, 1, 2. And in this case, they're L and M sub L, and it's a little more complicated to visualize. But hopefully this one makes sense. If you look at this math function right here, the constants out front are just normalization constants. They come from doing that inner rule I spoke of, and you square it. Well, what does cosine squared look like? Well, when theta is equal to 0 up at the top there, cosine is 1, cosine squared is 1. When you come down so that theta is equal to 90 degrees, cosine of 90 degrees is 0. And so that's why along that direction, there is no probability that it'll be in the equatorial plane. And as you keep moving down to the South Pole, okay, the cosine of pi, or 180 degrees, is +1. Square that, it's still +1. So there's a great probability that it'll be in those lobes that are above or below the equatorial plane. On the other hand, if you look right there and you square that guy, well, up at theta equal to 0, sine of 0 is 0. At 180 degrees or pi, sine of 180 degrees or pi is 0. But in the equatorial plane, well, in that case, that's 90 degrees, pi over 2 radians. Sine of that is 1. And so hopefully you're able to do some sort of kind of visualization from this of what sine of theta looks like. And a little harder to see, but you can work out, hey, what does sine squared look like? What does sine cosine look like when you square it? And what does this other Legendre polynomial here look like? And see if you believe these were done. Now, these were done in Mathematica by one of my friends, and I'm very confident that that's what the picture looks like. But now you're able to see, in angle anyway, what the greatest probability of finding a particle, an electron, going around a proton in a hydrogen atom. All right, I think I want to just quickly leave this idea. Yeah, because I got to go now to the other piece, which is the radial solution. Okay, and so I'm flipping gears here, and we just finished talking about this equation right here. Its solution, our Legendre polynomials, associated Legendre polynomials, P, L, M sub L, listed on a table, okay, or listed as another table on these spherical harmonics, which are also a function of L and M sub L, right? We want to work with the other half of what I've got here, okay? The thing that was on the other side, I want to manipulate that. And so I want to come up with a radial equation and show you what the solutions to that are. And hopefully I gave myself a little bit of room to work here. No, I didn't. So I'm going to go back to the angular solution that we were just talking about right here. And we finished up on the left-hand side. Let's now work with the right-hand side. Okay, so I'm going to take that thing. And remember, we set that equal to the same constant that we did the right-hand side. This guy is going to be equal to L times L plus 1. All right. Slide that up here a little bit. And I think what I'm left with. Yeah, okay, I got all the pieces there. I'm going to try to write it so I can see both. 1 over r times the derivative with respect to r of r squared times the derivative of r with respect to r plus 2 times the reduced mass over h bar squared times r squared times the difference in the total energy and the potential energy has to be equal to L times L plus 1, the constant that we chose for separation here in both cases. Actually, I'd already written it once, hadn't I? So we can get rid of that guy. All right, let's manipulate that a little bit, get it in the form that I want it to be in. The first thing most people do is exactly what I did with the theta function, which is f multiplied by r. So the derivative with respect to r, come on, pen, it just decided to turn itself off. R squared dr with respect to r plus twice the reduced mass over h bar squared r squared e minus v times r, because I'm getting rid of that guy, okay, is equal to L plus 1 times r. And now in the same vein as what I did earlier, I think I want to divide everything by 1 over r squared. I'm going to get rid of that guy. And I want to bring that term over to the other side of the equation. So I'll write 1 over r squared, derivative with respect to r of r squared times the derivative of r with respect to r, plus twice the reduced mass over h bar squared. And now I just have total energy minus potential energy times r. And then I guess I'll subtract off L plus 1, also divided by r squared, right, times r, and set that equal to 0. Okay, almost done. And it'll be in a form of the mathematician, physicist who worked on it. 1 over r squared, derivative with respect to r of r squared dr. Okay, plus, and I'm going to factor this guy out, twice the reduced mass over h bar squared. And I'll just have E minus V. We'll go with a square bracket here, because out of the other side, I'm going to factor out the function R. And so what'll be left here? It'll be minus h bar squared over twice the reduced mass times L plus 1 over r squared. I think I got that where I want it. Yes, 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 yes. All right. And this particular equation right here has a name, just like the one that was only a function of theta was called the associated Legendre polynomial. The one I just worked up right there is referred to as the associated Legendre equation. Again, another French mathematician funded by Napoleon who made his life's work solving that equation. I think I really want parentheses right there. That's how I left you off on the previous slide. I think he solved that equation. And what do the solutions look like? Well, I think we're almost going to have to wait till Wednesday to see. I don't have a great table. Where am I? There, solutions of the radial equation. The associated Legendre equation has these solutions, and it's conventional for people to take this term right here and apply a product rule to this guy right here, right? It's the first times the derivative of the second plus the second times the derivative of the first, and you get these two terms, okay? And then I absolutely put in for what the potential is for Coulomb. And right now I'm just working the L equals 0 case, if you're wondering where that L times L plus 1 went, okay? And according to the angular equation, that would mean that M sub L also has to be 0. And so you can get a feel for what the equations, the solutions to this guy look like. They're going to look like decaying exponentials in space. And that's where we're going to pick up on Wednesday. We'll actually see if that does solve the differential equation with some constant A0 and some normalization constant capital A. And we'll see if that actually does work and what results we get. And the results we get hopefully will be familiar to you. All right, looks like my time is up. I'm going to stop recording right here.